Hi, my name is Leah Kiner. I'm a PhD student in the Autonomous Vehicle Systems Lab at CU Boulder under Dr. Hans-Peter Schaub. And today I will be presenting the paper from the 2026 AAS GN&C conference titled Generalized Backsubstitution Dynamics for Branching of Free Rigid Bodies Attached to Prescribed Components. Okay, so this research is motivated by the fact that spacecraft are more complex than ever. We've seen missions rapidly advancing since the inception of the space age with the launch of Sputnik in 1957. We've seen solar-powered systems rapidly advance from being rigidly attached to our hub, which was first flown on Pioneer 5 and the lunar orbiters. And these solar-powered systems quickly advanced to being articulated to track the sun, which was first flown on Mariner 10 in 1973. And then finally, most recently, the Lucy mission, which was launched in 2021 to explore the Trojan asteroids, is the first spacecraft to fly these flexible substrate arrays, which deployed using a motor-driven lanyard. It's really interesting to see how far we've come and how these spacecraft have evolved. And along that same vein, we've also seen advancements in robotic arms being launched into space. These arms are now dominant tools used aboard spacecraft to assist in orbital servicing, docking, assembly, and astronaut EVA operations. The first generation of the Canadarm was launched aboard the Space Shuttle in 1981, and the second generation was launched aboard the ISS in 2001. And these two arms work together to actually assemble the ISS, which was first launched in 1998. And the International Space Station is perhaps the most complex spacecraft to ever be flown in space. And then finally, the OSIRIS-REx mission, which was a sample return mission to the asteroid Bennu, which launched in 2016, deployed this telescoping robotic arm to collect samples from the surface of the asteroid. And so, what I wanted to highlight here with all of these missions is the fact that these missions would not have been possible without incredible advancements in modeling and simulation of spacecraft structures. And these aspects of modeling and simulation are fundamental to the mission design process. They are necessary for analyzing and validating the expected performance of the spacecraft across the different phases of the mission. And it is extremely crucial that these simulations for these different systems are as accurate as possible to really truly capture the dynamics of these systems once they are launched into space. And as we're seeing these spacecraft grow in complexity, it becomes more and more important to accurately simulate these systems because the actuation of one component can have a dramatic effect on the attitude and rate of our spacecraft. So typically, first we derive the equations of motion for these types of complex systems. We can use Newtonian and Eulerian mechanics, which is a force and torque-based method. We can use Lagrangian mechanics, which is an energy-based method, or we can use Keynes' method, which uses concepts of generalized forces. Once we arrive at our system equations of motion, we must then verify and validate those equations to prove that the model is both correct and that it obeys the fundamental laws of physics, and that the model is also truly representative of the system that we are studying. However, the most important question here, which has been deeply studied over many years, is really how these derived equations are implemented or organized in software. This decision really has a dramatic effect on many different aspects of the software, from how maintainable it is long-term, to how scalable the software is, how easily testable different blocks of our software is, and also finally how fast or efficient our simulation can run. So there have been many different algorithms that have been developed for simulating multi-body systems. This research focuses on the back substitution method, which was introduced in 2018 by Dr. Cody Allard and Dr. Hans-Peter Schaub. This is the most spacecraft-specific algorithm of all of these different formulations that have been introduced. It assumes a hub-centric spacecraft design to perform Gaussian elimination on the equations of motion, which avoids inversion of the entire system mass matrix, which in turn improves the efficiency of our simulation. And then finally, its software implementation is modular, centralized, rapidly scalable, and easily testable. So it really has all of the features that we're looking for a dynamics formulation. Okay, so just more of a background on this method. Most spacecraft that are launched into space contain a central structure that's rigid, and so we call that our hub. It's seen in gray here, and it has this B-frame attached to it. And so we're interested in solving for the hub's inertial accelerations in our simulation. So we typically need to invert our mass matrix to resolve those accelerations. So the main assumption of this method is that the components, also called effectors, these components can be solar panels, reaction wheels, or thrusters. But the main assumption here is that once we derive a formulation for a specific component, we can then only attach that component to our central hub structure. We cannot attach one component to another. And so while these components can consist of multiple rigid bodies, when we derive or when we draw a bounding box around the system of bodies that we consider a single component or effector, we then must attach that specific component directly to our hub, because if we want to attach that to another component, we introduce additional coupling terms that we do not account for in the original formulation. So this main hub-centric assumption does improve the efficiency of our simulation, which I will now talk about. So we can write the equations of motion of our system in this form, where the left-hand side is our mass matrix multiplied by our state acceleration vector, which contains our hub accelerations and the accelerations for our effector degrees of freedom. And the right-hand side is all other terms. And so the hub-centric assumption of this method gives us this general mass matrix form here. So the upper left is our hub-on-hub contributions. The upper right, the pink, is the impact of the effector's accelerations on our hub equations of motion. This lower left blue quadrant is the impact of our hub's accelerations on our effector equations of motion. And then finally, under the assumptions of this method, all of our cross-effector contributions must be zero, which enables us to invert smaller portions of this mass matrix to improve the efficiency of our simulation. So just to highlight what I mean there, here is our equation of motion form. For each effector, we can bring all of our terms to the right-hand side, so we can isolate our effector accelerations on the left-hand side. We can then back substitute our effector accelerations into our hub equations of motion, which are the first two rows there. And then we can come to this compact form here, which we can use Schur decomposition to only invert two 3x3 matrices to solve for our hub accelerations here. So now that we have our hub accelerations, we can back substitute those into our effector equations of motion. So now we can fully resolve the accelerations of this system and numerically integrate our equations of motion. Okay, so previous work has derived many different formulations to model different components that we can attach to our hub. We've seen formulations for reaction wheels, variable speed CMGs. We've also seen formulations for single, dual, and N-hinged solar panels, and also fuel slosh models. And then more recently, we've also seen formulations for N-body serial chains of rotating or translating components, which can be used to simulate robotic arms in space. However, the main limitation of this method is that hub-centric assumption. So we can recall that these components or effectors can consist of multiple rigid bodies. However, this method requires that these effectors be directly attached to our hub. So this configuration in this bottom right image is not allowable currently to simulate because we see component attachments to components that are not our central rigid hub. And so these component-on-component attachments cannot be simulated because we have additional cross-coupling terms that are not captured in the original equations that we've implemented in software for these effectors. So currently, if we did want to derive the equations of motion and simulate this five-body system attached to our hub, we would need to sit down and analytically derive the equations of motion for this five-body component. And you can imagine how tedious and time-consuming that would be, especially if each of these bodies has an arbitrary number of degrees of freedom. It would be extremely tedious to develop those equations. And so we really want to avoid that at all costs. And so the question that this research is asking and answering is how can we enable general attachments to prescribed components using the back substitution method? And so this green truss structure that I'm showing in this unallowable configuration is a prescribed component, which I will talk about on this next slide. Um, Okay, so I wanted to illustrate the original capability of this method by using a tree structure. So our central hub of our spacecraft is corresponds to the trunk of this tree. And so originally, the original assumption of this method is that we attach those regular effectors that I showed directly to our central hub. So we see these blue shrubs that are attached directly to the trunk of this tree here. And so previous work derived or modified the back substitution method to enable simulation of prescribed components that are attached either to one another or directly to our central hub. And so these prescribed components are different than these original effectors because these original effectors have degrees of freedom associated with their motion, whereas these prescribed effectors, while they may have kinematic degrees of freedom, they contribute no equations of motion to our system. And so they, in turn, contribute no degrees of freedom to our system. So we are explicitly forcing the kinematic motion of these prescribed components. And so that was previous work. And so most recently, we also enabled simulation of branching of these original effectors, of select original effectors, so attachments of these blue original effectors to our prescribed components. And so in this work, what we are now seeking to do is develop a completely generalized effector that now can act as an umbrella to simulate all of the original effectors in blue. And so we are looking to simulate a general 6 degree of freedom rigid body. So we can really configure any type of rigid body motion that we can either attach directly to our central hub or that we can branch on top of a prescribed component. But first, I wanted to talk about this most recent work, which was enabling branching of these original effectors attached to a prescribed component. Okay, so recent work has modified these existing formulations in software to enable branching of these existing effectors, which are attached to a prescribed component. So currently in software, we have single body branching for translating components, which is this purple body, a one-DOF spinner, which is this blue body, and then also a two-DOF spinner, which is that upper figure. And so in this way, because we are modifying these existing effectors in software, we can easily toggle branching on or off for each of these effectors. And so this avoids any duplication of code because rather than analytically rederive the equations of motion for these branching configurations, we are simply modifying these existing effectors in software. Okay, so I just wanted to highlight this, just this one-DOF rotating body and really show how we derive those equations. So here are the results. Here are our left-hand side A, B, C, D terms, and the right-hand side contains all of those other terms in our hub equations of motion. And so we can see that we modified the existing effector with these highlighted additional coupling contributions. So we can toggle this branching attachment to a prescribed component on or off. So we can really easily either simulate this one-DOF spinner attachment to the prescribed component or our central hub by whether or not we include these highlighted terms in our equations of motion. Okay, so we have applied these existing effectors to different branching scenarios. So this left image or video highlights the 1DOF and 2DOF spinning bodies, which are attached to these long prescribed trusses, which are rotating relative to our hub to simulate an ISS-like structure. And then this right video is an asteroid lander scenario where we are simulating branching of these 1DOF translating bodies, which are these three deploying struts. And we see that this prescribed platform is deploying away from our hub. And then after that prescribed deployment is complete, these translational struts deploy away from our prescribed platform. Okay, so now in this paper, we are investigating development of a completely generalized effector to enable simulation of any type of 6 degree of freedom rigid body motion, either relative to our hub or relative to a prescribed component. Okay, so in this way, we are developing a new back substitution formulation for general 6 degree of freedom rigid body branching. We use a joint mapping formulation to enable any type of rigid body motion to be configured. We can simulate 1DOF rotation, 1DOF translation, a 1DOF screw motion, which is coupled translation and rotation, or any combination of these different types of motion up to 6 degrees of freedom. And so the interesting part about this new general effector is the fact that we can simulate all of these previously developed effectors with this one generalized formulation. Okay, so to do that, we use a concept called joint maps. So we can see this upper left image is a 1DOF rotating body attached to our hub. The upper right is a single axis translating body. The lower left is a 1DOF screw, which has coupled translation and rotation. And then this lower right is a 2DOF rotating and translating body. And so we can see that we can map the degree of freedom of each of these components directly to our hub relative velocities of this component. And so although the right-hand side of these expressions all do look different, we can introduce a generalized joint mapping matrix T, which is 6 by n, and then n is the number of degrees of freedom of this component attached to our hub. And then this beta vector now contains a list of the degrees of freedom of this specific component, which is n by 1. So now we can unite the representation of all of these different effectors using a single general rigid body here. And so we can now use this general mapping formulation to derive the equations of motion for this type of component. And so applying that to branching now, we have several different frames of reference. We have an inertial reference frame. We have our hubs frame B. The frame of our prescribed component is this P frame, which actuates relative to our hub, relative to this intermediate mount frame M, which is also rigidly attached to our hub, which is introduced as a convenience frame if it's easier to profile our prescribed component motion relative to a different point that does not coincide with our hubs frame. And then finally, the frame of this general component is this G frame. So here are our results for our system translational and rotational equations of motion here with this general joint mapping formulation here. And so these coupling contributions disappear when we instead attach this general body to our hub. And this is because what remains is what we would traditionally implement in software, where we don't have any additional coupling terms for any component on component attachments. If we remove our general body, what remains is the equations of motion for this prescribed system. And then if we remove our prescribed component, we have the equations for a general component attached to our rigid hub. Okay, so we also had to draw a bounding box around this general component and apply Newtonian and Eulerian mechanics to resolve the up to 6 degree of freedom equations of motion for this general body. So here are the results there for the translational and rotational equations of motion for that general component. And we can then write these equations of motion in this compact form here, which we can then back substitute into our hub equations of motion, which I showed on the previous slide. And we arrive at this formulation here, where here are our ABCD terms on the left-hand side, and then the right-hand side is this vectrans and vecrot, which is quite complicated. But now we can really see that using this joint mapping formulation, we can simulate any type of component branching relative to a prescribed component. So that was what was introduced in this paper, and then future work involves expanding the single general body derivation to n bodies that we can either attach directly to our hub or to a prescribed component. Okay, thank you so much. And if you have any questions, feel free to reach out to myself or my advisor, Dr. Hans-Peter Schaub. Thank you so much.